In this video, we're going to build the best transformer translation system. What's going on, guys? Hope you're doing awesome. So in this video, we're going to create sequence transformers. Previously, I've made videos on vanilla sequence and sequence with attention using LSTMs. And now we're going to take the next step and build it with the transformer model. So what we're going to do is we're going to use Pytorch inbuilt transformer modules to build our network. But if you want to see how to understand and build a transformer network from scratch, I've also made a video that you can check out on that. Anyways, enough said already. Let's just get started with the code. So the first thing I'm going to do is cheat a little bit, and I'm going to just copy in the imports. So we're going to have the import torch as normal. We're going to have the end module. We're going to have the optim module. Then we're going to have spacey, which if you watched my previous videos is for the vocabulary and the tokenizer. So for the data processing, essentially. Then we have from utils, which is a function I've created. And these are just nice functions to have. I didn't feel they are a necessity, so I didn't include them in this video. But so it's just for calculating the BLEU score so that we have an estimate of how good our model is when we're done. And then saving the model, loading the model, and then also a function for translating a sentence. So if we send in a string, then it's going to return the translated sentence for that input. And then we also use TensorBoard to get some nice loss plots, and then multi30k for the dataset, which is a dataset of German to English, and then torch text for the data processing, essentially. So now we're going to set up the data processing part, which I've done in the previous videos as well. And I'm just going to put timestamps if you've already watched this part, and you can skip it. But for those of you who hasn't, we're just going to go through it step by step. So what we're going to do first is we're going to load our vocabulary. We're going to do spacey.load of DE. We're going to do this for the German vocabulary. And then we're going to do spacey English, which is spacey.load of English. And if you don't have those, I'm going to copy in how you would install them. So you would just do Python m spacey download en for the English one. And then we want to create our tokenizer. So we're going to do define tokenize German, and we're going to just send in some text. And then we want to return tok.text for token spacey ger.tokenizer of that text. And then we're just going to do define tokenize of English. We're going to send in some text again. And then we're going to do return tok.text for token spacey ger.spacey English.tokenizer of that text. All right, great. And then we're going to create our field for the torch text. Yeah, so I guess if you don't know torch text and you want to know more about it, I've also made videos on that. So, but we're going to use field, which is essentially setting up how the data should be processed. So then we're going to do German equals field. We're going to set the tokenizer. So we're going to do tokenize equals tokenize German. And then we're going to set so everything is lowercase. We're going to do lower equals true. We're going to do init token. We're going to set the init token to just SOS for start token. And then end of sentence token, we're just going to set to be EOS like this. And then we're pretty much going to do the same thing for the German one. The English one. So we're going to do field tokenize equals tokenize English, lower equals true. And yeah, so I guess the same thing. And then we're going to get our training data. So we're going to do train data, validation, and we're also going to get our validation data and then our test data. And we're going to do multi30k.splits. And so we're going to do, let's see. Yeah, so we're going to send in first the extensions. We're going to do .de, and then we're going to do .en. All right. And then we're going to do and then we're going to do fields, and then we're going to do German, and then we're going to do English. So essentially this is saying that we're going to have the German one for the first one, and then we got to map the corresponding field for that language. And then also the English one, we're going to send the English one. So it's important to have the order correct. And then what we're going to do is we're going to build our vocabulary. So German.build vocabulary. We're going to do the train data. We're going to do send the max size of 10,000 of our vocabulary size. Minimum frequency, we're going to set to 2. And then I guess we can copy that in. And I guess we can do it like this. And then we can do English.build vocabulary. And same thing. And then we're just going to create our transformer now. So we're going to do class transformer, and we're going to inherit from the NN module. We're going to create our init, and we're going to do self. We're going to send in the embedding size. We're going to send in the source vocabulary size, the target vocabulary size, and then the source pad index, the number of heads that we're going to use for the attention mechanism, and then the number of encoder layers, the number of decoder layers, forward expansion, and all of these are going to make sense if you watch the transformer from scratch or if you know about transformers. And then we're going to send in the dropout, and then the max length, and then the device that we're going to use. And then we're going to do super of transformer, and then self, and then dot init. And the first thing we're going to do is we're just going to create our embeddings. So we're going to do self.source word embedding is going to be nn.embedding. And we're going to send in source vocabulary size, the embedding size, self source position embedding. So we're going to have, the embedding for the words, but to make it aware of the positions of the word, since transformers are permutationally invariant, we're going to add this positional embedding. So we're going to do nn.embedding. Then we're going to just send in the max length, and again map it to the embedding size. And similarly for the targets, we're going to target word embedding, nn.embedding, and we're going to do target vocabulary size, and then embedding size. And let's see, so we're also going to do self.target position embedding. I'm going to do nn.embedding, and then the max length, and again map it to the embedding size. And we can also set stuff like, we can also set stuff like self.device equals device, and then we can call we can create the transformer. So this is quite easy. We don't have to build it from scratch now. We can just use Pytorch own implementation. So we're just going to do self.transformer equals nn.transformer. And we're just going to send in the embedding size, the number of heads. And I mean, this is ridiculous. If it took us 1 hour to code it in the last video for, making it from scratch. So anyways, number of encoder layers, number of decoder layers, and then we can have a forward expansion and the dropout. And let's see. So now we have the transformer, and I guess there's one more thing missing, is that we're gonna have to have the linear layer. So we're gonna have self.fcout. We're gonna have nn.linear embedding size, and we're gonna have the target vocabulary size. And self.dropout, we're just gonna do nn dropout of dropout. And we can also do self.source pad index, source pad index. All right, so we've essentially set up everything we need for the transformer network, right? We created the transformer here, the linear layer mapping to the vocabulary so that we get our output, and all of the embeddings. There's one more thing that we need to do, in that we need to create the masking. So remember, we have a masking for the target, and we can use Pytorch. They have a function for doing that, and then we can also make a source mask. So we're going to make both of those, and I don't think they have a function for making the source mask, so we're just going to do it. Make a source mask. We're just going to send in source text, and again, this is just for making we can skip some of the computation essentially. If we have padded it, then there's no need to compute for those padded values. So we're gonna do source mask equals source. We're gonna do first source.transpose 0 and 1, and we're gonna do equals self.source pad index. So the reason that we do transpose right here is because when we send it in, it's going to be, so source shape is going to be source length comma n, but the transformer that Pytorch has implemented takes it as input, so the opposite. So we need to do a transpose, and then we just do equals source pad index. So the output would be n comma source length in shape, which is what Pytorch transformer wants it to be. So then we're just going to do return source mask, and we're going to do the forward part, and we're going to send in source and also the target, and we can get source sequence length comma n equal to source.shape, and then we can get target sequence length comma n, which is going to be target shape. And the first thing we're going to do is we're going to create the positions for the position embedding. So we're going to do source positions, and we're just going to do equals, and let's see, we're going to do torch dot arrange 0, and then source sequence length. So essentially we're just creating like a tensor of 0, 1, 2, 3, 4, etc. just for the positions. And then we're going to do dot unsqueeze 1 to add a dimension. And then we're just going to do dot expand target sequence length, and then comma n, just so that we have it for every example that we send in. And then we're just going to do dot to self dot device. And we're just going to do the same thing for the target positions. So we're going to do equals torch dot arrange 0, and then we're just going to replace that with the target sequence length like that, and then unsqueeze 1, and again dot expand target sequence length comma n, and then dot to self dot device. All right, now that we have the positions, which are going to be used for the position embeddings, we can do embed source, which is going to be self.dropout, and it's going to be self.source word embedding of source, but it's also going to be the position embedding, and this is what creates so that the network is aware of the order of the words. If we don't have this part right here, the self position embedding, then the network is, if you change the order of the words, the output is going to be exactly the same. So this part is really important. We're just going to send in source positions, and then we're going to do embed target. We're going to do self.dropout. We're going to do self.target word embedding of target, and then we're just going to add self.target word embedding. So same thing. Then we're going to create our masking. So we're going to do source padding mask is self.make source mask, and we're just going to send in the source. Then we're going to create our target mask, and we can use an inbuilt function that Pytorch has in the transformer module. So we're going to do self.transformer for calling that module. Then we're going to do .generate square subsequent mask. I really think they should make this, like, they could make this function call a little bit shorter, I feel like. And then we're just going to do target sequence length, and then .to, and then we're just going to do self.device. Okay, so now we got everything. So this, remember, these are all sort of the essential parts that we need to send into the transformer that we define up here. So now we're just going to use those and we're just going to send them into the transformer. So pretty easy in that way. We're just going to do self.transformer, and then we're going to send in the embed source, the embed target. We're going to do source key padding mask equals source padding mask. And then the target mask is just going to be the target mask. So those, we're just going to send those in by keyword argument. And then at the end, we're just going to return out. All right, so now really we've created a model, and now we're just going to create the training phase of the network. So you know what we're going to do now is we're going to set up the training phase. So really this is just going to be, you know, we're going to set the device, torch.device, CUDA, if torch.CUDA is available, else we're going to set it to the CPU. All this is pretty standard, I guess. Then we're going to do load model. We're going to do false because we don't have a model to begin with. But we're going to, you know, if you've saved the model, then you can put true and it's going to load the model. And we can do save model equals true. And then we can do some training hyperparameters. We can do sort of the number of epochs. Let's set it to 10 or 5 maybe. And then we can do the learning rate. 3e minus 4. And then we can do batch size equals 32. We can do model hyperparameters. And that's, so we can first define the source vocab size. That's just going to be the length of the German vocabulary. Then we can do the target vocabulary size. And again, that's just going to be the English vocabulary, since we're translating from German to English. And then the embedding size, we're going to set to 512. Number of heads, we're going to set to 8. And these are all pretty standard values. I think that's what they used in the attention is all you need paper. Then we're going to do number encoder layers. And I think they used 6 in the paper, but we're just going to use 3. And then num decoder layers, we're just going to set to the same. Dropout, we're going to use like 0.10. I think for sequence to sequence, the dropout is usually tend to set a bit lower than for using fully connected or something like that. So we're just going to use 0.10, and then the max length is going to be 100. And remember, the max length is going to be the sentence length, which is we don't have any source length or target length larger than 100. And this, the max length is used for the positional embedding. So that's very important. So for example, if we would have sentences that are longer than 100, we would have to delete them or increase the max length. And then let's see, we're going to do we're going to do forward expansion equals 4. And then we're just going to get our source pad index, which is english.vocabulary.string to index. And then we're going to get the pad index, pad token. All right, so we can also get TensorBoard for nice plots, stuff like that. And we can do writer equals summary writer. And we're just going to set it to the folder runs. And then let's do loss plot. And we're going to do step equals 0. Just, that's just for the TensorBoard. All right, so let's create our iterator. Right? We have our training data, and that gets the data, but we need to get get data loader so that it can do the batching, and it's also going to do the padding for us, which is super convenient. So we're just going to train iterator, validation iterator, test iterator. We're just going to do bucket iterator dot splits, and we're going to do train data, validation data, test data. And this is very important that you match these. So the validation data is the second argument, and the validation iterator is the second output. And then we're just going to do batch size equals batch size. We're going to do sort within batch equals true. And this is just so that if we have 32 examples sent at the same time, and then it makes sense that all of them should be of equivalent length, so that we don't have to do that much padding, because that would be unnecessary computation. So that's just for a little bit more efficient computation right there. And then we're going to sort key lambda x, and we're going to sort it by x.source, so the source sentence length. And then device, we're just going to set to device. All right. Then we're going to call our model. We're going to set model. We're going to call the transformer. We're going to send in all of the embedding size. We're going to send in source vocabulary size, target vocabulary size, source pad index, and and then we're going to send in the number of heads, number of encoder layers, number of decoder layers, forward expansion, dropout, max length, and then the device. And then finally, we're going to do .to device. And let's see what more. We're going to create the optimizer and opt-in.atom. We're going to do model.parameters. We're going to do learning rate equals learning rate. And yeah, you could also create a scheduler. We can skip that actually, but you could also create a scheduler. Pad index, we're just going to do English.vocabulary string to index. We're going to do pad. And the reason why we do this is because when we create the loss function, so we do criterion equals nn.cross entropy loss, we're going to do ignore index equals pad index, so that those aren't relevant for computing the cost. And then we can do if load model, load checkpoint, torch.load, and the file I save it in is just my checkpoint.pth.tar. And so this comes from the util function that I import. And I've made a video on how to save and load model as well. But yeah, I guess this is more of an advanced video as well, so you probably know all of that stuff. And then the model, and we're going to send in the optimizer. That's just how I created the load checkpoint. And let's see, then we're going to do so we're going to have an example sentence, and I'm just going to copy that in actually. So that's just an example that I have right there to see that it's doing the right thing. And I think that sentence is something like a horse is walking beneath a bridge beside a boat or something like that. And then we're going to do for epoch in range of num epochs. We're going to do print. We're going to do we can do something like this, epoch, like that, just to illustrate the epoch in a nice way. And then we can do if save model. We can do checkpoint is equal to state dict is going to be model.state dict. And then we can do the optimizer, and that would just be the optimizer.state dict. And also that should be an underscore. Then we can do save checkpoint of that checkpoint. And also what we could do is we could do model.eval, and we're going to use that util function translate sentence. So we're just going to do translated sentence is translate sentence of, we're just going to send in the model. This isn't really that important. It's just to get some nice output so that we can see that it makes sense what it's doing. Let's change this to 100. And then we can do print of translated example sentence. And we're just going to do backslash \n, and then we're just gonna send in the translated sentence. All right, and then we're gonna get it back to model.train. We're gonna do for batch index, comma batch in enumerate train train iterator. We're gonna first get the input data, and we're just gonna do batch.source, and then we're gonna do .toDevice, and then we're gonna do target is gonna be batch.target.toDevice. Then we're gonna do the forward prop. So we're gonna do forward prop output is gonna be model, and it's just gonna be the input data, and then it's gonna be the target, except that we're gonna remove one thing. And so the reason why we're doing, up to the last one is because we want the target, the target that we sent in and the corresponding output from that target in the transformer. We want there to be a shift so that the first sort of the output is one time step or one element ahead of the input for that corresponding time step. So essentially, when we send in the first element of the input to be the start token, we want it to the first output from the transformer to correspond to the second element in the target. So that's why we do that. And then we're gonna do output. We're gonna do output equals output.reshape. So remember that if we have a batch of, let's say, 10 examples, then for every example in that batch, we have a predicted translated sentence of, let's say, 50 words. And for each of those words, we have another dimension in the output equal to the target vocabulary. And this corresponds to the probability for each word in the vocabulary. So to make cross entropy work in this case, we're gonna have to concatenate the batch, all of the examples, with the words, and then keep the last dimension, which is the target vocabulary size. So how we can do that is we're just gonna do -1, and we're just gonna keep the last dimension of the output shape 2, and then we're gonna do target is target 1 and then the end, and this is also because we want there to be a shift of 1 between the output and the target. We want the output to be 1 ahead of the target, and then we're going to do reshape, and we're going to do -1, since this is just going to be a single long vector for every target word that we want, the index for every target word. Then we're just going to do optimizer.0grad, and loss is equal to criterion of the output and the target. We're going to do loss.backward, and then we're going to do width, we're going to do torch.nn.utils.clip_grad_norm, and we're just going to send in the model parameters, and we're going to do set max norm equal to 1. And so this is just to avoid exploding gradient problems. And then we're going to do optimizer.step. We're going to do writer.add for the tensor board, writer.add scalar, and then the training loss. We're going to do the loss, and then the global step is equal to step. We're just going to do step plus equals 1. And let's see, we're also going to do, in the end, after training is done, we're going to do score equals BLEU from the util function. We're going to do test data. We're going to do model, German, English, and device. And then we're just going to do print BLEU score. And then we're just going to do score times 100. And we're going to do just 2 decimal places, so .2f. And essentially, so this is going to take quite a while. So this is going to take a while. So to keep that in mind. But now we have everything ready. We have the entire training phase. We have the model. Yeah, so we've created everything now, and hopefully, if there are no errors, this should work to run. But probably there are. Let's see. So it's just going to download the data set. Yeah, and then in the cross entropy loss. So let's see, what line was that? In line 162, we're going to do not ignore index, we're going to do ignore index. So ignore index, and then let's rerun it. Yeah, and here for the source positions, we're not going to do target sequence length. We got to do source sequence length. So there was a typo right there. Yeah, and then right here, source pad index, and that should work. So let's rerun it. And then we get another very scary looking error right here. But luckily I was able to find the problem, which was that in the model, in the transform model, the out here is from self.transformer, but we need one more, which we created as well, the fc out. So we're gonna send that in. We're gonna do out equals self.fc out of out, and that should probably, hopefully, be enough. So let's try and rerun this. One thing that doesn't cause an error, but is an error nonetheless, is that this thing here with the target word embedding should be target position embedding, like this. So training it for a couple of epochs, we see that it's from the beginning, it's super random, roller skaters, peppers, reporter, and then, you know, after just one epoch, it's pretty much perfect. So a horse walks next to a boat, oh, okay, so that's not perfect, but it gets the gist, right? And then in the next epoch, I think it's pretty much dead on. So a horse walks under a bridge next to a bridge. Yeah, okay, almost. So in the next epoch, then a horse walks under a bridge next to a boat. And I think that should be the exact correct translation. And yeah, this one is in the training data, so that's why it learns it so quickly. But anyways, what I'm gonna do is that I've actually trained this network for a bit longer, and I'm just gonna do, I'm gonna try to load that model, and then we're gonna take the BLEU score from right here. We're just gonna copy that in, and we're just gonna skip the training phase, and we're just gonna put it something like this, and we're just gonna exit straight afterwards. So we're just gonna load the model that I've trained for a couple of more epochs, not too long, but and then we're just gonna see what is the BLEU score for this model, and then we can, you know, compare it to the sequence with attention, and then the sequence model. Yeah, and I just realized now that this my checkpoint.pth.tar, it should not be, it should just be .tar. So the trained model got a BLEU score of 35.27, which is a lot better than what we did for sequence to sequence, you know, using LSTMs and with attention. If I remember correctly, I think we got 20 a BLEU score with a vanilla sequence, and then 27 or 28 with the sequence with attention. So, you know, getting a BLEU score of 35 is a massive improvement, and I even think this model has room to improve. So I think this one can even improve further if we train it for longer. So I think that puts an end to these sequence videos that I've done now that we've done the transformer model. And hopefully this video was useful, and thank you so much for watching.